Restream has failed us. Okay, everybody. Take two.
Take two.
And and now we are recording as well because for the first time ever, Restream failed me, and I lost all of my channels on Restream, unfortunately. Um,
Oh,
but we're back. We are here. Um, let's just Hello and welcome to the program. I'm Carl Pauls. I'm here with Chris Bergen and our special guest, Daniel Chen. Daniel is
hi.
a PhD student of nuclear engineering at Ontario Tech who brings us insight about the past, present, and future of atomic energy development. Hopefully, Restream stays stable for us this time, but just in case, I'm going to record from here on out for Gabe so that we can upload directly. It's disappointing when that happens. Uh, Welcome
Oh
back,
well.
Daniel. I introduced us in our earlier or late rehearsal. Let's call it late rehearsal. There are countries who have nuclear mining capability, nuclear or uranium production capability, like Australia, Canada. In fact, many countries using seawater extraction could have nuclear uranium for their own plants, for their own reactors. But the question is, why don't more countries do enrichment, especially Canada? Canada has some of the best proven reserves of uranium in the world. So I apologize again for the problem streaming, but take it away, Daniel.
All right. Hello everyone. Today we're going to discuss a cost analysis of enrichment in Canada, and then probably try and lead the conversation where it leads us, I suppose. Right. And so before we talk about cost analysis of enrichment in Canada specifically, let's sort of bring it more, make the subject broader. Let's talk about what the fuel supply chain looks like, what Canada's place is in it, right? So most people, when they talk about nuclear fuel supply chains, they talk exclusively about mining, and that is important, right? But it's not the only part of the front end of the nuclear fuel supply chain, right? So you begin with mining, which is where you extract uranium out of usually rocks, as right now, right? And you extract it as uranium oxides, which are ceramic materials that is not too much unlike the material that is used to make your teacups, for an instance. It's radioactive, except that's radioactive, right? Then what you do is you do a process known as conversion, right? And what that means is that you have uranium oxides, which is a ceramic. You turn it into uranium hexafluoride. Uranium hexafluoride is sort of physically similar-ish to table salt, except that it is table salt that evaporates at 5,500 degrees. It is also something that you do not want to put on your food because it is very radioactive and very toxic chemically as well, right? The reason why you want to turn it into a hexafluoride is because you actually want to evaporate it and then put it through an enrichment process. During enrichment, you are extracting the fissile fractions, the U-235, out of your bulk uranium, right? Once that U-235 is extracted, again in hexafluoride form, you then do something called deconversion, which is where you turn the hexafluoride, this table salt-like material, back into a ceramic, right? And ceramics are stable. That is what you make. That is what goes into the final process of the nuclear fuel supply chain, which is the fabrication of fuel rods, fuel bundles, fuel assemblies, whatever you call it. It's the big shiny stuff, the fuel that you actually put into your reactor, right? So you have these 5 processes. Which ones do Canada do? And before we get into that, I suppose let's talk about uranium mining, right? There has been people who are concerned about, you know, uranium from Russia, and there are people who tell you that Russian uranium is not a concern because Russia doesn't actually mine that much uranium, and you kind of wonder how could that be? These two can't both be true at the same time. Well, actually, it can, right? See, with mining, Russia actually doesn't do that much mining. It's somewhat substantive at 8%, but it is a reasonable distance from the three top countries of where uranium is sourced, right? Namely Australia, Kazakhstan, and indeed Canada. Incidentally, Canada, mines quite a bit of the world's uranium, I suppose, but really not that much, right? Compared to this, let's talk about conversion, right? This is a chart showing the world's conversion capacity as of 2020. You'll notice that Russia and Canada are kind of at the top of the pack in terms of how much chemical conversion that they do. So the process that turns your uranium from like ceramics into table salt and then back again, right? And in particular, and this is somewhat unusual for Canada especially, because if you remember, the conversion process is mostly there to facilitate enrichment, right? And Canada does 30% of the world's conversion. So one wonders how much enrichment Canada does, and the answer is that Canada doesn't do any enrichment at all, right? The only players in world enrichment is CNNC, so Chinese nuclear in China. You have Orano in France, you have Rosatom in Russia, and then you have Urenco, which is extremely difficult to explain. Let's just call it Europe for now. And then everybody else picking up whatever scraps remain, essentially. Importantly, Canada is basically not on here, right? And so the actual Canadian placement within the global nuclear fuel supply chain is actually decently weird, right? Canada does quite a bit of mining. It does a whole lot of conversion, and it does no enrichment, which is why you're doing the conversion in the first place. And so Canada does this very strange thing where it creates a UF6, it exports most of it, it re-imports it back, right? And then because fuel fabrication is dependent on reactor vendors, essentially, and Canada doesn't use enriched fuel, it has to send the deconverted uranium oxides back out again for fabrication into fuel. Right. And, this is not ideal for many reasons because you are exporting and then re-importing hazardous materials. And also, the value is going into other countries as a result. And so in an ideal case, you'd want, Canada at least would like to have mining, conversion, enrichment, and deconversion in the country so that most of the value is retained there. And then the good stuff that pays the enriched UO2 is the only stuff that is shipping out to reactor vendors for fabrication into fuel.
Chris has a question, so why don't you go ahead, Chris?
Yeah, just actually two very brief questions.
Sure.
Well, brief questions. I hope the answers are equally brief. Does Canada, does the form that they're processing take, is that actually yellow cake?
So yellow cake is, if we go back here, yellow cake is uranium that has been dug out of the mine and it has been dressed, so to speak, right? So when uranium oxides come out of the ground, it isn't pure uranium oxides, right?
Mm-hmm.
It has a lot of dirt and other junk in it, right? If you remove that dirt and junk, usually physically, then that's called yellow cake. And yellow cake is the stuff that goes into conversion. Sometimes, although it's rather rare these days, it's also the stuff that comes out of deconversion, right? But essentially, yellow cake is purified uranium oxides. It's not quite the thing that comes out of the mine. It's not quite the thing that goes into the fuel, but it is close to both of these things. I hope that answers your question.
It's like a primary ingredient into the fabrication process.
Kind of. You can,
Okay.
if we are making an analogy with, let's say, steel smelting, the yellow
Mhm.
cake is a bit like the purified iron ore,
Mhm.
right? That's kind of what it is.
Okay. Okay.
So
And my
hopefully that answers
second
your question.
question,
Yeah.
I've heard this was on another podcast, maybe
Mhm.
the decoupled podcast. I don't recall exactly, but I've heard that Canada does enrich fuel for their can do's, but they enrich them only to like 1, maybe 1.5% for the neutron economy. But they don't need to, but they occasionally do for some fuel bundles.
They don't.
They don't?
Um,
Absolutely. Okay.
no. So Canada has Canada enriches, but not in commercial quantities, right?
Hmm.
Canadian nuclear plants, for the most part, use natural uranium fuel.
Hmm.
Canada has dabbled in wanting higher enriched fuels, but that has not worked out for the most part. And it is,
Okay.
you know, it was something that was this, the using enriched fuels in CANDUs. This is known as the so-called advanced CANDU reactor, or the ACR. This was discussed around 2020-ish. Then you had 2022 with the war in Ukraine, and then everybody stopped talking about that. So yeah, essentially, Canada does not do enrichment at commercial scales.
Okay. And does that include the research reactors?
Canada has research reactors that use enriched fuels, possibly up to HALEU. I'm not entirely sure, but Canada does not supply that enriched uranium, as far as I'm aware. And
Okay.
if our conversation gets us there, there was once a time when Canada had essentially bomb materials that it is converting into radiopharmaceuticals. Canada doesn't do that either, and Canada didn't supply its own high enriched uranium at the time, in any
Okay.
case.
Thanks. Sorry
Yeah,
to hijack everything.
no problem. So shall we continue?
Yeah.
Hmm.
All right. So ideally, Canada would like, well, I should say, it's not that Canada would like, Canada should like to, not have to export and re-import hazardous materials in and out and in, rather, from its borders. It like most of its the values that comes from the supply chain to stay in the country, right? It wants to get away with just selling the good stuff that pays to foreign customers, right? This is the Port Hope conversion facility in Ontario, Canada. It is, by the standards of Canada, I suppose, not that far from where my university is. The campus itself is actually about the same size, perhaps slightly smaller than the actual campus of Ontario Tech, which is not a big school to begin with, right? And this is where most of the conversion and deconversion that I said Canada does 30% of the world's supply of is in this facility, right? And it sort of ties back to what a lot of people say about nuclear energy, but they haven't really internalized that. Nuclear is a very energy dense energy source, right? A facility like this provides 30% of the world's fuel, at least as far as conversion facilities go. Right. So, onto the topic that I actually want to talk about, which is enrichment. Right. So, there are different ways of enriching uranium. Right. And to sort of begin, let's talk about this unit that's used to describe how much enrichment you do, which is called the separative work unit, right? And it is usually abbreviated SWU, sometimes pronounced SWU. And, you might see it, you don't quite understand what it does, right? So the idea behind separative work unit is that enrichment is somewhat bothersome in that one enrichment device, whatever it is, we'll talk about what those devices do and look like later, but sort of one device typically does not do much enrichment, right? So for illustrative purposes, this is a centrifuge. If you put in if you put in uranium at 0.72% enrichment, which is about natural levels, right? You put it through one stage of a centrifuge, you get out uranium that is 0.725% ish enrichment, right? So one enrichment device does not achieve much separation, right? And so to get all the way to 5% if you're doing LWR fuels, or even 20% if you want fancy halo fuels, you need to daisy chain a bunch of them together, right? Right? And so many devices need to be chained to achieve usable qualities of enrichment, right? In addition, one centrifuge isn't capable of producing tons and tons of usable fuel, right? And so in addition to stringing them together in series, you also need to put a lot of strings in parallel, right, to provide usable throughputs for your for producing however much fuel that it is that you want, right? And as a result, sort of the separative work unit is basically a way of taking both of these things into account. Intuitively, higher enrichment requires more separative work. Higher throughputs also require more separative work, right? And you can calculate exactly how much separative work you need through this fancy looking formula. It looks complicated because it kind of is, but the important point is that, you know, with the same amount of centrifuges, you can have, but even if you keep the same amount of centrifuges, you can have either high enrichment but less fuel, or less enrichment at more fuel, right? And so it is an apples to apples kind of unit where the number of devices that you actually need, all you need to do is calculate how much separative work unit you need versus how much separative work unit is provided per device, right? So to illustrate, right, if you are starting with natural uranium and you want to get 1 kilogram of light water reactor 5% low enriched uranium, right, you'll need 6.8, so nearly 7 separative work units to get 1 kilogram of fuel, right? And if you want to get the fancy HALEU fuel, right, and you want 1 kilogram of that, you'll need 35 separative work units. And so higher enrichment requires higher separative work units, and the amount of separative work units also scales quite linearly with how much fuel that you're trying to enrich, right? And as another illustrative example, right, enriching all the uranium converted that Canada does chemical conversion to, right, to light water reactor fuel requires on the order of about 9 million separative work units per year, right? And so just remember that 9 million number. We'll get back to it, right? So how do these devices work, right? The oldest commercial enrichment device is the gas diffusion cell. And what it is quite simply, you have a ceramic film that has a bunch of very, very small holes in it, right? And because uranium hexafluoride is a gas, it will diffuse through these tiny holes. However, U-235 is lighter, right? It literally weighs less than U-238. And so it permeates the film faster. Very, very slightly faster, but it is enough such that in one stage you can get slightly more uranium-235 at one end in the product stage and slightly less in the tailing stage. And, you know, as kind of mentioned before, this isn't much separation, and so you need to essentially daisy chain a bunch of these gas diffusion cells together in a very, very long string to get to the amount of enrichment that you need, right? Also importantly, because you are trying to push a bunch of quite a quite a lot of gas actually through a ceramic membrane with lots of tiny holes, this is going to take a lot of power, right? And so the efficiency of a gas diffusion cell is that you get 0.4 separated work units with 1 megawatt hour of electricity. To sort of illustrate this, 1 megawatt hour of electricity is roughly the total energy output of 5-ish average American homes in an entire day, right? So this this produces essentially 1 pound of this produces about 1/10 of a pound of light water reactor fuel. So it kind of gives you an idea of how energy intensive enrichment is, right? With regards to floor efficiency, you get 8.8 separated work units per year per centimeter per meter squared. So you imagine a piece of floor the size of your desk, right? And you run it for an entire year, you get about, it's enough to make you about 1 kilogram of fuel. So, the gas diffusion cell is very is not very space efficient or power efficient for that matter, right? Around 50 years ago, people started moving on to more sophisticated methods of enrichment, and that's the gas centrifuge, which is still the workhorse technology used today. Essentially, how the gas centrifuge works is that it works a lot like the spin drying cycle of your washing machine. So you have an inner tub here that spins the gas very fast. Right, and much like the spin dryer of your washing machine, the heavy stuff, everything gets flung towards the sides, but heavier stuff gets flung harder, right? And so, all else being equal, the gas in the center of your barrel essentially is filled with the lighter U-235, and again, it's not much more U-235, but it is slightly more. Right. Whereas the outer edges of the outer peripheries of your barrel is slightly depleted in U-235 and has more U-238. Right. And once again, this is a very minute difference. And so what you typically have to do is you have to have a bunch of these centrifuges in a very long daisy chain to get to 5% enrichment. Right. And if we compare the power efficiency, you notice that the power efficiency is substantially better in a gas centrifuge than in a gas diffusion cell, because you're not pushing lots and lots of gas through tiny holes anymore. Most of this energy comes from actually turning your spin dryer, right? In terms of floor efficiency, it's a lot better as well, in no small part because as opposed to the diffusion cells, these actually stand upright, and they're also sort of very.
That is much more. That is like 50 times more efficient. I did some quick comparison. The previous method would, for 5 days of energy consumption, produce 1 year of energy demand, and this one is 52 years of energy demand. So that's basically like 2 weeks of energy consumption. You have produced enough uranium to fuel you for your entire life.
Yep.
Amazing.
And so this is so the gas centrifuge was developed about half a century ago. It is still the workhorse today. We do have better, right? So this is sort of the latest and greatest in enrichment technologies. This is called laser isotope separation, right? And the way that it works is that perhaps I don't know if it's probably high school chemistry. You're told that different isotopes are chemically identical, and that is a lie, right? Different isotopes actually differ very, very subtly in chemistry, right? It is so subtle that conventional chemical methods where you're using, test tubes and acids and so on, do not really separate isotopes. However, you can induce chemical excitations by fine-tuning a laser, right? And the laser can be tuned enough that it can essentially ionize certain isotopes, but not others, right? And so this is kind of a cartoon of how laser isotope separation works. Essentially, you vaporize either uranium metal in this particular case, or you can vaporize the uranium hexafluoride, right? You shine a laser that selectively ionizes the U-235, right? And because it's ionized, it carries charge. If you have an electric field crossing the cloud of vapor, essentially, that's coming out, then it will selectively draw out the U-235 and not the U-238, right? And this differs from the previous process in many ways. Chief among them, one stage of laser isotope separation separates the isotopes quite cleanly, right? And so you don't need a daisy chain of a bunch of devices, of like tens, maybe hundreds of devices. You probably only need like a handful of stages to get to the cleanliness that you need. In addition, and sort of because of this, first of all, the power efficiency is drastically improved. Laser isotope separation has not been commercialized, so we don't actually know how power efficient it is, but based on laboratory prototypes, you can sort of approximate it as being perhaps 10 times more efficient in terms of both power use and floor use, right? And so this is kind of the latest and greatest. How do they compare in terms of cost? Well, annoyingly, cost estimates for enrichment is not very open to the public, right? This is kind of the most detailed cost analysis that I can find, and it is for the gas diffusion technology, which is kind of considered obsolete now. It is also from a study that dates back to the 1970s, so it's of sort of dubious relevance right now, right? But the amount of separative work unit that that this hypothetical plant produces is roughly about the amount that would cover the enrichment capacity required to cover all of Canadian inversion, essentially. So about 8.75, so about 9 million separative work units, right? And once again, sort of, this is, I'm not an economist, right? And so I can't sort of comb through this report to try and extrapolate this cost estimate to other technologies in too much detail. However, being the good engineer I am, I'm going to fudge it, right? So you'll notice that most of the cost comes from the feed, right? Which I am discounting in this case because Canada already converts, right? So it is cost that Canada is already spending, essentially, right? You have capital cost, which is associated with interests for loans for the huge amounts of money that you're going to actually build the plant, right? And I'm going to assume that this scales with how much floor you're using, right? Because it kind of makes sense to imagine that, if your factory covers more floor, then it is going to use more money to build stuff over that floor, right? I'm going to assume that power use scales with power because duh, right? And sort of the cost that's covered in others. So imagine this to be sort of maintenance, paying staff and so on. I'm going to assume that this stays the same, except that this report, as mentioned, was done 50 years ago. And so, one thing that has changed a lot compared to 50 years ago is inflation. So, 1970s dollars is not modern dollars, right? So if we sort of do that very rough if we sort of do a very rough cost analysis based on those assumptions, then and based on sort of power and land requirements that we mentioned last time, then to enrich all of the UF6 produced in Canada, right, would require costs that is technology dependent, and to sort of see how well we did, I suppose. This is kind of market values. And I guess somewhat fortuitously, our values for the enrichment cost for the centrifuge is roughly coincides with the lower bounds of the market value. And this makes sense because centrifuges are the main technologies used in the global in the global supply chain. And so you sort of imagine that the cost of running the centrifuge is about the lower bound of what the market value is supposed to be, right? And you'll also notice that the gas diffusion cell is much more expensive, basically not competitive at all, whereas laser enrichment is much less, and therefore possibly very much more cost effective, right? What this all means is that there's literally hundreds of millions of dollars that could be made in Canada, but isn't, right? And in fact, this is floor use as drawn on Google Maps, right? This is the Port Hope facility. You'll notice that, if we want to cover Canadian enrichment, that basically involves demolishing the entire town of Port Hope if we are using gas diffusion technology, right? If we're doing centrifuge technology, then that means that we are essentially doubling the area roughly of the Port Hope conversion facility. Whereas if we're going with laser enrichment, then the Port Hope facility doesn't actually need to change very much at all. To put it a very succinct way, right? Port Hope can make millions of dollars per day by vacating this parking lot and filling it with lasers, right? And so that brings up a very good question. Like, this is economically very great for Canada. Why isn't Canada doing this, right? And, as with most things in Canada, the answer typically is that America doesn't like you doing this, right? This is George Bush addressing, I believe, the US Senate and various other political dignitaries within the US, basically saying that enrichment and reprocessing are not necessary for nations seeking to harness nuclear energy for peaceful purposes. In plain English, what that means is that Bush believes that making nuclear fuel is not necessary for making nuclear energy. Bizarre as it seems. And, it isn't unique to Bush either. This is an excerpt from a Senate debate during the Obama era in 2014. Yeah, 2014, I believe, right? And, the senators are basically saying that the policy of US nuclear exports, right, is to pursue 123 agreements, so nuclear export agreements, that minimize the further proliferation of ENR, that's enrichment and reprocessing technologies worldwide, right? And basically what that means is that the reason why the US exports nuclear reactors is to minimize nuclear fuel production, right? And, I guess that kind of makes sense. It isn't as though that, and this is not just in violation of basic logic. It is, in fact, in violation of international treaties, right? This is Article 4 of the Treaty of Non-Proliferation of Nuclear Weapons, right? And it says very clearly that every country has the inalienable right, assuming they've signed the treaty, to develop, research, produce, and use nuclear energy for peaceful purposes without discrimination, right? And in fact, the formulators of the NPT specifically want advanced civilian nuclear technological capabilities in the territories of non-nuclear weapon states party to the treaty, right? And so not only does it seem strange that you're trying to discourage other countries from making nuclear fuel despite also wanting them to buy your reactors. This is literally against the law, right? In both spirit and letter, right? And then to make matters worse, you have this situation where the IAEA and the US basically colluded with the Russian government, right, to move all of enrichment to Siberia, right, as part of what's known as a multilateral non-proliferation measure, right? Because as we all know, multilateral means that you're concentrating everything in one country, and non-proliferation means that you're handing it to a nuclear weapon state, right? I don't know what can possibly go wrong with that. So in conclusion, right, does Canada need domestic enrichment? And the answer is no. I think that as an answer to, I can't remember if it was Carl or Chris's question, Canada does not, like Canadian nuclear reactors are specifically designed to not require enriched fuel, right? So Canada does not need domestic enrichment. That said, should Canada have domestic enrichment? And, opinions may vary, but my answer is yes. And the reasons are that, first of all, it is a lot of money. It is also, not pointlessly exporting and then re-exporting hazardous materials, which Canada already creates, by the way, right? It enhances global security of the nuclear fuel supply chain so that not everything is concentrated in Russia. And then you have, political and moral difficulties associated with whether or not you want to actually embargo Russian uranium, right? It also enhances the global non-proliferation regime by exercising the inalienable rights granted by the non-proliferation treaty, right? So if everybody thinks that they're getting goodies out of not proliferating, they're less likely to proliferate. And finally, and the biggest one, the US has screwed up big time, right? They violated the law, they violated basic knowledge, they murdered basic English, and it is Canada's duty and privilege to set their southern neighbors right, at least in my opinion. And so I think I've reached the end of the slide, and so I'm going to invite questions and further discussions about this, I guess.
That's kind of amazing. What I think I want to start with is, what is the non-proliferation risk of everyone getting laser enrichment technology? Because right now there might be a case that, we would know as soon as a enrichment facility goes online because it uses so much damn power, but at 1/10 of that demand per unit, it would be a little bit harder to detect. Or what's the scale involved to reach, let's say, the 20% mark?
So this is, so within sort of non-proliferation orthodoxy, I suppose, this has kind of been the sticking point of laser enrichment, and why, despite the fact that it was developed in sort of late 70s, early 80s, it never came online, right? With both gaseous diffusion and also centrifuge technologies, right? You are required to daisy chain at least a couple of dozen devices, and possibly hundreds of devices in the case of the gas centrifuge, right? To get from natural uranium to bomb-grade materials. And in contrast, the laser isotope separation, no one really knows how good it, no one publicly knows how well laser isotope separation performs. But you are sort of looking at on the order of maybe 2 stages to get from natural uranium to LWR fuel, right? And then maybe half a dozen more stages to go from that to bomb-grade materials. And so one of the things that I really dislike about non-proliferation talks with regards to enrichment, and especially laser isotope separation, is that you're saying that something should be banned because it's too efficient. And that makes the engineer in me die inside.
Right. Yeah.
And to sort of And to sort of strengthen my point as to why I think this is unwise, despite the fact that it will increase weapons proliferation risk if everybody is allowed to do laser isotope separation, right? So once upon a time, actually, let's not start with once upon a time. Let's start with right now. There is a radioisotope called technetium-99m, right? And it is a radioactive element. It is a radioactive isotope that is used in radiopharmaceuticals, mostly for diagnosing cancer, and I think it might be used for treating cancer as well, right? Vitally important. Vitally important part of radiopharmacology. And once upon a time, Canada made 90% of the world's technetium-99m, right? And now they produce essentially none of it, right? Because the way that you created technetium-99 is that it is a fission product. And so what you did was you took a lump of uranium and then you put it in a nuclear reactor, irradiate it, right? You take it out, you dunk it in acid, you dissolve everything, you use chemistry voodoo essentially to extract the molybdenum, interestingly, which then decays to the technetium that you want, right? Now, the problem is that if you are dissolving irradiated fuel, it is easier to get at the stuff that you want if there isn't a bunch of unfissioned materials inside your fuel, right? And what that means is that the enrichment of the what's known as the target, so the stuff that you're putting into the reactor, is very high. It is essentially 100% enriched uranium that Canada puts into its reactors to create radiopharmaceuticals, right? And prior to the 2000s, the US didn't like it, but they're going to have to be okay, right? Because Canada is a US ally, and also Canadian nuclear reactors can facilitate you putting weird stuff into the reactor without shutting the reactor down, which is not a feature that light water reactors have, right? And then during the early 2000s, there was something involving a plane flying into buildings that got the American policymakers extremely freaked out for some reason. And as a result of this, they basically said that we aren't we aren't exporting, essentially 100% enriched uranium to Canada anymore. We aren't going to be exporting 100% enriched uranium to anyone, right? Because that will increase security. And of course, guess where all the technetium-99m is being produced now?
Russia?
Yep.
Oh, man. How did I guess?
Yeah. So yeah, it's kind of, so to sort of go back to your question, I suppose, does laser isotope separation increase non-proliferation risk? That depends, doesn't it, right? On the one hand, it does increase proliferation risk in the sense that it gives the capability of countries to get bomb-grade materials. On the other hand, right, is that necessarily a bad thing? Would you rather sort of risk Canada maybe doing something fishy that they shouldn't be doing with the pure uranium-235, essentially, that they are using? Or would you rather all of that technology be confined in Russia and all of your radiopharmaceuticals, essentially, is being held hostage by Russia?
That's the geopolitics of it, isn't it?
It is, right? It's also something that I really dislike about non-proliferation discourse, because non-proliferation discourse is mostly run by nuclear engineers, and nuclear engineers are very uncreative, shall we say, when it comes to geopolitics. So
I'm running an experiment. Let's go for 10 minutes. I am, of course, afraid that if I loop my browser and the Zoom meeting, it'll cause problems on your end, that you'll hear your own voice. But I just opened a x.com space, a Twitter space, to do Q&A, and we did get one person who showed up, and if anyone who is in this space raises their hand, I'll try to get the question in, but I'm going to relay the question through Zoom with my voice.
Of course.
But so go ahead, and if anyone is in that Twitter space, I've linked it. If you go to x.com/Carl Alex Pauls, you can join us. You can join the Twitter space. But I don't know if anyone else is going to show up or if anyone listening is going to raise their hand. So, Chris, do you have any questions?
Only question I had was the location of the Hope Processing Center. Was that southeast of Montreal, near the Canadian or near the Atlantic Ocean?
No, it is on the shores of Lake Ontario. It is about let's call it 100 to 200-ish miles from Toronto.
Okay.
Yeah.
So, given the United States need and dire need for enrichment, trying to divest from Russian enrichment, why aren't we pursuing laser isotope separation?
So there's sort of two parts to that question. I'm going to answer the easy part, the one that I know how to answer. Specifically, if you are asking specifically why the US does not pursue laser isotope enrichment, there is actually an open letter by the American Physical Society about a specific version of laser isotope enrichment called SILEX, right? And they basically argue that America should not be using it because it's too good, right? It uses so little floor, so little power that, in principle, right, so-called rogue nations can essentially fit a bomb factory in a basement, and the US would not be any the wiser. Now, I have issues with this. First of all, the fact that you shouldn't use something because it's too efficient kills the engineer that's sitting inside of me. But moreover, it's like so-called rogue states, they already do that, right? In fact, back in the day, the US also made a bunch of bomb materials in basements, right? It's not something that is substantially facilitated by having more efficient technologies, right? To answer the other part of your question, which is, I guess, kind of implied, why doesn't the US just do enrichment? The answer is, I don't know, right? My understanding is that the US essentially had a bunch of gas diffusion cells that's left over from first the Manhattan Project and then the ensuing Cold War, right? And as we kind of noted, gas diffusion is not economical compared to centrifuges, which were starting to take off in Europe at the time. And Canada, and so essentially the US said that's okay, because it was the 1970s. Laser isotope enrichment was starting to be invented and experimented upon in various US national laboratories. The US at the time thought that they were just going to essentially piggyback to that, and also, reprocessing and breeder reactors. And then you had the late 80s, early 90s, where the Soviet Union collapsed. And then there was just suddenly a bunch of first of all weapons grade materials coming out of Russia, and also a bunch of enrichment capability also coming out of Russia, right? And so they basically and so essentially it's just much cheaper for a very, very long time to essentially be buying both enriched uranium and also MOX fuels from Russia, and there was no economic incentive essentially to have to build centrifuges in the US, right? And later on, it was discovered that despite being the latest and greatest, the US isn't going to pursue laser isotope enrichment anymore because, and again, this kills the engineer in me, it's too efficient. So yeah, that's kind of as far as I know as to why people don't. Yeah.
But essentially, if we're talking about the new meta when it comes to geopolitics, we have enormous constraints around centrifuging, enrichment, and technology trade. We banned companies from working with China on nuclear projects. We're not allowing these things to be exported. So I think it's perfectly acceptable for a place like Oak Ridge or Pacific Northwest to be involved in this process, in the government itself through the national labs providing enrichment services. And guess what? We've got some wonderful partners in fuel fabrication who are not too far from these national labs. I think it's, within our mission to save the planet that this technology could be developed within the bubble of national security because it provides for our energy security.
It's kind of a chicken and egg problem, I suppose, because the way that I'm understanding sort of the politics around enrichment, specifically in the US right now, is that you mentioned that it is the it is the mission of the US to save the world, and that depends a good deal on whether the world agrees, right? So in particular, if you are enriching, are you just enriching for the US's needs, or are you enriching for the sake of tripling global nuclear expansion, right? And keeping in mind, of course, that this tripling may involve a bunch of Russian reactors, right? And if the answer is going to be yes, then it is going to make me profoundly sad, because I do not want Taiwan or Canada or any other country to be dependent on US fuel, right? However, economically it would work out, right? However, if the answer is going to be no, right, then you have a chicken and egg problem where no one wants to build reactors that requires fuel that doesn't exist, and no one wants to be making fuel for reactors that don't exist, right? So you have a chicken and egg problem over which comes first, the reactor or the fuel, right? And incidentally, to sort of bring things back to Canada for a bit, I suppose, the Canadian nuclear industry was invented by people with a lot of foresight, right? The CANDU reactor is, on paper, not a great reactor. It is bigger, it is more expensive, it uses more fuel, it creates more waste than other reactors of the same power, right? The moderator also has a propensity to create a bunch of tritium, which is, not impossible to deal with, but kind of a headache, right? However, the pioneers of the Canadian nuclear industry said, yes, we know all that. We don't care, right? Because what we want is a reactor technology that can be built using Canadian technological capabilities, right? So no heavy forging. There are no big reactor vessels. The CANDU reactor is a series of tubes, to paraphrase Obama, I suppose, right? And it also involves no politically problematic technologies, mostly enrichment, right? It is, and uranium oxides can just be dug out of Canadian soil and actually fabricated in Canada. And in fact, that's mostly what Canada does, right? And so, in terms of like, I guess what I'm trying to get to is that in terms of energy policy and energy security policy in particular, sometimes cost is not the it is not the first consideration that countries have. It isn't the consideration of Canada. I believe that for many countries that are looking into nuclear, it is not going to be the first consideration of that either, right? It's not going to be how much the fuel cost. It is where the fuel is coming from.
Well, let's get to a really wonderful comment from Sean Noyes on Facebook. Sean comments, Silex and GLE have continued to accelerate construction of a full-scale laser and separator equipment being deployed in GLE's test loop facility in Wilmington. And then he also mentions a Paducah project. Yeah. And so it sounds like Silex is pursuing a TRL-6 facility in order to get laser separation produced as early as right now, mid-2024. And so this is essentially amazing and perhaps breaking news for at least one of us here. But yeah, it's pretty fascinating to hear that this might be happening.
Yeah, I mean, I'm perhaps less optimistic about that, I suppose, because Silex was Silex is pretty recent, but laser isotope enrichment has been investigated by U.S. national laboratories, like I said, in the late 70s, right? And it was not deployed in the late 70s, not because of any technological difficulties, but because, because bombs in basements scare U.S. politicians, I guess, right? And there is nothing about Silex that fundamentally resolves that problem, right?
Right. And
one of the jokes that I often, one of the things that people sometimes ask me is, why am I studying nuclear engineering in Canada and not the U.S.? And I say, well, the problem with the U.S. is that the U.S. develops a bunch of really excellent and very fun technologies in their university and their national labs with the explicit aim of getting it banned. And laser isotope separation is one of those things. What I am going to be I'm going to just jinx everything because I don't care anymore, right? But as soon as Silex actually gets proven in the US, assuming it ever does, it is going to get banned because it works too well.
Well, that's
and that
great
might not
news.
be the stuff and that might not be the excuse given to the press, but it will be what's going to happen.
I think I've cracked the code. I think you're right. That must be why Australia is developing it. Silex is an Australian company, apparently, and they're shipping.
So Silex.
Go ahead.
So I am going to rant about us.
I got a rant here. You stepped on my punchline. I'm making the joke that the anti-nuclear forces in Australia are secretly working for Silex so they can develop and finalize this technology so that Australia can help ban nuclear energy efficient development. That's the punchline.
Okay. So my punchline is kind of similar but different. So Silex is not being developed in Australia. Silex was invented in Australia, right? And it is now being developed in the US, apparently.
Okay. So they've transferred operations.
And essentially what happened was that you had two professors from the University of, I'm going to say Sydney, but don't quote me on that, right? They basically just they basically just created Silex in their lab, and then they basically handed the patents to the US. And this is where I think that and sort of this is where the punchline comes in, where I think that this is because Australia is so anti-nuclear, they handed it to the US to get it banned, right? If they wanted this technology to be used everywhere, they should have just handed it to China.
Ooh, you got the joke.
Right. And it's not like China is going to proliferate Silex to its client states, right? But the US is going to, but this is certainly going to be a fire on the backsides of US policymakers to basically essentially recreate the technology in the US and then possibly using it, right?
Mm-hmm.
Anyway.
Excellent.
Yeah.
Well, it looks like we're not going to get any questions in our Twitter space, but this is sort of a capability that I'm going to test out. I might try to run this on like a laptop or someplace separate so I can route the audio better. But it's looking like we'll be able to do this. We'll be able to do audience Q&A via Twitter. So follow me on x.com/CarlAlexPauls. You will see this program as well as the Twitter space for Q&A immediately following every Sunday at 10 a.m. Pacific, 1 p.m. Eastern. As a reminder, this is the Eco-Modernist channel. Go ahead.
I'm kind of seeing two interesting questions on YouTube, apparently. Yeah.
I see. Yeah. Okay, go ahead and address those.
Sure. So one was, why not just ask Urenco or Orano to provide gas centrifuges? That's an interesting question. I got another interesting. I'm going to answer the Urenco question first. So with regards to, there's sort of two dimensions to the why not Urenco question. The sort of from the global perspective first, right? Let's take the example of Niger, right? Niger was a country that prior to the military coup that they had quite recently, they were supplying something like 20% of Europe's uranium in the form of mining, and something like half the fuel that is used in Canada, again in the form of mining, right? And despite the role that they played in providing European and French nuclear energy, right, they were basically getting essentially 2% of the value of the fuel supply chain, right? And this is something that nuclear advocacy, cough Mark Nelson, cough, is extremely proud of. You jerkasses, right? This is colonial exploitation, plain and simple, right? And so to answer the answer of why not Urenco or Orano, right? There are developing countries that have some very strong feelings about their colonial masters, of which Urenco and Orano is a part of. Let's just say, right? There is ongoing exploitation by these people and by these organizations, right? That makes it unacceptable for a bunch of developing countries that people claim that they want to exploit nuclear to, right? So that's sort of the global perspective. In terms of for the US specifically, why not just Urenco or Orano? There is a very interesting blog post by Jacques Delvaney from Thorcon, which goes into that. But essentially, foreign countries are banned from doing enrichment or reprocessing on US soil. Even though that kind of doesn't make any sense, because those countries already do enrichment and reprocessing in their own countries. And it is something that Jack Delvaney complains about at length, and I'm not going to either steal his thunder or risk talking about legal stuff that I don't quite understand myself, but that's kind of why Urenco or Rano does not is not unproblematic solution to the uranium shortage that we have. Right. There was somebody who asks. There was Hamstray on YouTube who asks, why are they, I'm going to assume that they are US policymakers, why are US policymakers so scared of Canada? I don't know, but it is true that 200 years ago, Canadian troops did march south and burn down the White House. Maybe that has something to do with it. I wouldn't know. Sean also asks, can you compare and contrast molecular laser isotope separation versus atomic laser isotope separation? So that's a very technical question, I suppose. So the difference between the two is that, go back to presentation mode.
Oh,
just so let me get this is there. The is it showing up?
No, just a sec.
Yes.
On my side, I need to. There you go.
Okay. So this is sort of the schematic for a generic laser isotope separation scheme, right? And the difference between atomic versus molecular vapor is that you are essentially trying to vaporize uranium-containing materials. And there are sort of two broad classes of which materials you can choose to vaporize. It can either be uranium metal, or it could be uranium hexafluoride. Now, the metallic uranium vapor is investigated first because conceptually it is more simple, right? In that it only has one type of atom and that's it, and you don't need to worry about weird chemistry in the vapor space with regards to that atom. However, first of all, uranium melts at something like nearly 900 degrees Celsius, right? Sorry, it boils at about 900 degrees Celsius. And so sort of getting the uranium to vaporize is extremely difficult compared to UF6, which, as we noted, vaporizes at 50 degrees Celsius, right? The other problem with the uranium, with uranium metal specifically, is that liquid uranium metal dissolves other metals, in particular iron, right? Which means that if you tried containing the molten uranium inside a steel crucible, then that is a bit like trying to contain hot coffee in a mug made out of sugar cubes, right? Your steel vessel is not going to last that long, let's just say, right? And so the uranium metal is very aggressive to most materials that you're going to make the device out of, right? And in comparison, uranium hexafluoride it's still poisonous and corrosive to certain things. It's not quite as weird about it as metallic uranium is, but sort of the price that you pay for that is that the chemistry of uranium fluorides, and especially uranium hexafluorides, is a bit strange. And you might have, you're trying to draw away you're trying to draw away the charged stuff, but there are different types of charges that can occur with uranium with uranium fluorides that does not occur with uranium metals. And so sort of the chemistry, so to speak, becomes harder with uranium hexafluorides, but the materials problems become harder with atomic vapor. And that's kind of it, basically. It's a technical trade-off, pick your poison. I suppose one of the other advantages of molecular laser isotope separation is that UF6 is used in the fuel supply chain as it exists today, right? Whereas metallic uranium is basically not used by anyone in a civilian context anymore. I think the Brits used to use metallic uranium fuel in their Magnox reactors. Certain types of breeder reactors also use metallic uranium fuel, but most of the commercial reactors do not use that. And at no point in the supply chain as it currently stands does uranium metal exist. And so you're essentially having to do extra special conversion to create the metallic uranium that you're going to have to be enriching out of. So, yeah.
Wonderful. Well, I think we've got a good consensus here now on the different gas diffusion technologies versus laser technologies, and this has been a wonderful piece of content, and I thank you for introducing us to laser isotope separation. I hope that we get some action on this, because it sounds like the kind of thing we really need to improve the case for nuclear, improve the case for American enrichment, and in fact, increase the availability of nuclear fuels across the world.
Mhm.
Yeah.
Thanks so much.
Arguably, like, it's not something that we only very briefly touched upon on this talk, but it is the subject of previous talks, right? Part of increasing availability is increasing diversity of suppliers. And by diversity of suppliers, I mean more countries should be allowed to have this technology, right? And in no small part either, because this is what the Non-Proliferation Treaty dictates, right? Countries should be allowed to enjoy all parts of the nuclear supply chains for peaceful purposes without prejudice, right?
Right.
And it kind of, sort of, it brings into question, perhaps, right, why these countries would continue abiding by a treaty for the non-proliferation of nuclear weapons if, the promised goodies are not being delivered, so to speak.
Wonderful. Thank you, everyone. Oh, go ahead, Chris. Last words.
But I was just gonna say, it sounds like the laser isotope would put it within reach of many other countries, economically and possibly, for other technical reasons, make it much more easier for more countries to have it, so that all countries could share in nuclear technologies going forward.
Arguably so. And it's something that I touched upon both on this talk and previous talks as well, right? Whereby, the non-proliferation people are concerned about rogue states making nuclear bombs in basements. Well, guess what? Rogue states have been making nuclear bombs in basements. In fact, the US had been making nuclear bombs in basements, essentially, right? Laser isotope
underneath stadium courts, etc.
Yeah, something like that. It's it's kind of like, you need several stages of centrifuges or gas diffusion cells to get to that level of enrichment, right? But remember the other dimension of how many devices you need, which is total throughput, right? And just to reiterate, you need hundreds of tons of fuel to run a civilian nuclear reactor, right? You need tens of kilograms, right? So 4 or 5 orders of magnitude less material to make a nuclear weapon, right? And so it doesn't matter if you are using it doesn't really matter if you're using hideously inefficient processes, right? The US started with the US started with the US started with calatrons, which is which is a very, very inefficient way of enriching uranium. But they got enough bomb materials made within a couple of years, right, to build the first to build the Little Man bomb, right? You also had South Africa, right, in the I believe it was the 80s, right, on the eve before they collapsed, right, using essentially they invented something called aerodynamic enrichment, which I didn't get into here, but it's kind of like it's a bit like centrifuges, but with microchips, essentially, right? To facilitate their nuclear weapons program, right? So bottom line is that the efficiency of laser isotope separation should not be used as an excuse to withhold it from other countries. And this is especially silly, at least to me, that it is being withheld in the US to stop it spreading to other countries. Like, that's not how technology works, especially not these days. So, yeah.
Wonderful. Okay. Thank you very much for your comments, your content, everyone, your insights into this field, and helping us make a better world. This has been the Eco-Modernist Channel Live. We broadcast every Sunday at 10 a.m. Pacific, 1 p.m. Eastern, right here on x.com/CarlAlexPauls. You can find us on Patreon at the Eco-Modernist Channel. You can find us on YouTube at the Eco-Modernist Channel. You can find us on Facebook at Eco-Modernist Society of North America. And you can find us on on the web at esna.earth. That's esna.earth. Again, thanks everyone for your contributions. We're going to be back here every week. Hopefully, get Gabe back on the continental U.S. shore, and new guests to speak to you for the rest of the summer. Emissions first, peace and justice will follow.
I want to speak to you about a new organization called the Eco-Modernist Society of North America. I'm here because we are in the midst of a potentially monumental ecological crisis. It is only through a new environmentalism 2.0 that progress can be made. We believe that our only hope for human advancement and even human survival is through the exponential advance of science in the service of humanity. Eco-modernism is a new environmental paradigm which looks to reverse the fear of nuclear power and scientific progress in general. Ecology-based modernism is the most direct way to define it. Eco-modernism as a philosophy is described in the Eco-Modernist Manifesto. We believe humanity should not be rejecting technological progress, but rather separate our impacts from nature through the responsible use of technology and urbanization. Urbanization is an unstoppable worldwide trend and the best solution to many environmental problems. It offers sustainable development for the human population and is a historic antidote to both deforestation and species extinction as humans move away from using wildlife as their protein source. Vertical, urban, high-rise architecture minimizes the use of land, resources, and energy, enabling walkable cities that facilitates the more efficient use of mass public transit as well. It must be emphasized that our support for technological solutions is definitely not about defending industrial polluters, nor does our defense of technology imply that we just need to sit back and let things take care of themselves. To the contrary, we believe that humanity is at a crossroads that severely threatens our future on this planet. I hope by now you understand the worthiness of our cause. Eco-modernism is really only a philosophy at this time. I want to talk to you about the necessity of turning it into a movement, which will be part of the larger environmentalist movement. For it is only through our presence and participation that there can be any hope of moving environmentalism in the right direction. Our aim is not to divide the environmental movement, but rather to multiply its numbers with the incorporation of many scientific and educational communities that is working to both build chapters of eco-modernist societies and support our growth worldwide.